On behalf of the iCity team, welcome to our iCity Research Days webinar series, and thank you for joining us. I'm Dr. Judy Farvolden, Executive Director of the Transportation Research Institute at the University of Toronto, and your host for the iCity webinar series. First, just a couple of housekeeping items. The session is being recorded, as are all sessions of the iCity series, and the recordings will be shared. We will have Q&A following all of the talks. Chat has been disabled, so please use Q&A to pose your questions, and please do pose questions and pose them early. We have a hard stop every 30 minutes and can't respond to last-minute raised hands. iCity Research Days webinar series, June 2020. iCity Urban Informatics for Sustainable Metropolitan Growth is headed by Principal Investigator Professor Eric J. Miller, and I'm its project manager. iCity has a collection of fabulous partners, and it's a highly interdisciplinary collaboration among researchers at 3 universities: the University of Toronto, OCAD University, and the University of Waterloo. We are grateful for the support of our public sector partners, Waterfront Toronto, Transportation Services at the City of Toronto and the region of Waterloo, and our private sector partners, Esri Canada, Terranet, IBM Canada, and Celent. We could not have done it without their support, both financial and in many forms of co-creating and collaborating. iCity is funded by the Ontario Research Fund Research Excellence Round 7, and we're also great for ORF support for our unique project. Over its 5 years of collaboration, iCity has involved 108 researchers working in 9 projects organized in 3 themes and produced 94 publications and counting. Every ORF project has to have a youth outreach program, and our youth outreach partner is the excellent Maximum City. You'll hear from them today. As I said, iCity research is organized around 3 themes. Theme 1 provides a foundation of ontologies and platforms, the subject of last Monday's talks. Theme 2 comprises a set of urban transportation applications in street design, parking, transit-oriented design, and integrated transportation and land use planning. These applications are the subject of the talks we'll see today, and they are activated by visualization and decision support tools created by our fine partners at OCAD University under Theme 3. We'll also see that collaboration today. This is the 4th in a series of 5 webinars. I hope you will join us for our last webinar this coming Wednesday. You can find details and register on the U-Tree website. Okay, today's webinar talks are on elements of the street and its users. And our first talk is a gamification survey approach to assessing parking and behavior. I'll say just a few words about each of our speakers, and you can find out more about them and all the speakers on today's panels on the information posted on the series on the U-Tree website. Dr. Mehdi Nourinejad is an assistant professor at the Civil Engineering Department at York University, but he received his PhD from the University of Toronto, so he's one of ours. Mehdi's research focuses on optimal planning and control of transportation systems in smart cities with autonomous vehicles. The parking work he will present today was among the many research contributions he made during his time at U of T. Wang completed his BASC and MASC at the University of Toronto, supervised, like Mehdi, by Professor Matt Roorda, with a research focus on parking behavior investigation, including survey design and multiple logit models development. Again, today, the subject of today's talk. Bo has no video camera, but you will hear him in the presentation in the Q&A to follow. Over to you, Bo.
Thank you. Hi, everyone. Thank you so much for joining us today. This is Mehdi Nourinejad, and I'm going to be talking about our research on street parking choice models using a gamification survey. So as you all know, actually, next slide, Bo. Yep. Great. So today we're going to talk a little bit about the introduction and the motivation for this study. I'll talk about the novelty of the new survey methodology that we're presenting here, and some of the modeled results and discussions and what we've concluded from this study. So parking is a very tedious part of auto travel, as we all know. To give you some statistics, drivers in the US spend an average of 17 hours a year searching for parking spots. In New York, it takes an average of 15 minutes to find a spot, and it costs about $33 to park for 2 hours. We have very similar statistics for other major cities in the world, In Toronto, I believe it's about 7 minutes. Downtown Toronto, it takes about 7 minutes to find a parking spot. So many cities are implementing policies to alleviate the burden of parking. The city of San Francisco, for instance, in 2011 initiated a pilot called SF Park that installed sensors in the pavement to collect parking occupancy information. So these were sensors in the pavement that would detect whether there's a car parked right above them or not. And the pilot disseminated that information collected from the sensors to people so that we would know where available parking spots are, and it would reduce our search time. In the city of Toronto, another policy was implemented called the Green P, that was pretty much an app that allowed travelers to pay for parking online on an hourly based parking price, and there are many, many others. So a lot of these parking policies, focus on guidance. Some of them focus on guidance information systems. If you've been to Yorkdale Mall before, they have these panels that tell you where to park, or we have parking reservation systems that reserve a parking spot for you. There are many, many different parking policies that are being implemented, both in the private sector and the public sector. And the objective is to reduce the burden of parking, or in some cases, generate more profit from parking. So if we want to devise useful and impactful parking policies, we first have to understand people's behavior. If you implement this policy, how are people going to behave with respect to that parking policy? To understand behavior, we need models. And to improve the accuracy of these models, we need to make them data-driven. We need to collect data from people, from travelers, and understand from that data how they behave with respect to different parking policies. There are two different ways to collect parking data, but these two methods have their own limitations that impede their ability to accurately model parking behavior. The first very common method is called the revealed preference method, in which we basically look at the choices that people made, and we use that information to calibrate our models. So as an example of this, if we mount a camera on the side of the road and we see where people are parking and how long they're parking for, we can use this data to somewhat calibrate the models that we have. The big problem with this revealed preference method is that we don't know the alternative options that people had when they chose a specific parking lot. We just know the one that they chose. We don't know the alternative choices that they had. So in the more technical terms, we don't know their choice sets. That's the problem we have with revealed preference surveys, the first method. The second method sort of fixes some of the issues with the first method because it asks people where they would have parked under special scenarios. So this is called a stated preference survey, where instead of seeing where people park, we ask them. We give them several scenarios and we say, if the parking price is this much, what would you do? If there's no parking spots available, what would you do? So it's a series of questions that we ask our respondents to be able to understand what their parking behavior is. The issue with this is that if you want to have a very comprehensive survey of what's happening, you have to ask them a lot of questions. And when you ask people a lot of questions, you create fatigue for the respondents, and you create bias in the way they respond to your questions. So these two methods, stated preference and revealed preference, although very useful in specific applications, for parking, they are a little bit, they're not as appropriate as they would be. So this was the motivation for our work. We know that these conventional methods are not very powerful in calibrating parking behavioral models, and we designed a new way that somewhat combines the strengths of these two methods and allows us to collect data and build models and devise impactful parking policies. I'm going to pass it on to Wolfram here.
Hey, thanks, Mehdi. I will talk about the iCity part survey in details and the modeling result. The survey in our project is designed as a simulation game state preference survey named iCity part, and it has 3 sections. The first section provides survey introductions, like the purpose of the survey, and then the second section is parking gameplay. It tells the players how to play the game, basically the instruction, and the parking scenarios that the player needs to find a parking spot in each of them. The last section collects respondents' demographic attributes in the form of multiple choice questions. And now I will discuss the game settings. In the game, the road network for the parking game is a 5x5 square grid network, and there are 4 possible initial locations shown by the red vehicle in the figure. The destination is set on a corner of the center indicated by the blue star. And the parking spots are distributed along 4 faces of all blocks. There are 8 legal parking spots in green and 2 illegal parking spots in red on each block face. And for the traffic conditions, it were considered at the beginning, while driving speed and parking task time frame impose related influence on the process of choosing parking spot. So a typical average driving speed in downtown Toronto is used for this survey. It's used to calculate the driving time from your initial location to the chosen parking spot. And then for walking speed, although it varies individually, the parking game considers an average walking speed to limit the number of variables. And it's used to compute the walking time from parking spots to destinations. The parking spots in the network are grouped into 5 alternatives based on their types and locations. The first and second one are legal and illegal parking spots in the red region, which are relatively close to the destination. And then the legal and illegal parking spots in the gray region are classified as alternatives 3 and 4. They are a little bit farther from the destination as compared to the spots in the red region. And then all other parking spots outside the red and gray region are classified into alternative 5. However, alternative 5 is considered as an invalid option because if the player chooses to park there, they wouldn't be able to arrive at destinations on time due to the time limit for their parking task. And there are 2 parking assistance levels in this gameplay. The first one is conventional parking. In this mode, the player can only observe states of parking spots around their current location with a limited distance. And in this parking level, respondents have to cruise around the destinations by directing their vehicles to gather parking information and then make parking decisions. This mode simulates conventional parking behavior. And the other mode is called assisted parking. In this mode, the players can observe states of all parking spots in the network, and which is shown in the figure. They can view the price or the hourly price, the availability by zooming in, and more details of all the attributes. So player in this mode first select the region and then zoom in for detailed information, and then just select parking spots to park. It's a representation of parking with assistance of PGI, which is Parking Guidance and Information System, and parking reservation systems, because drivers can obtain parking and arrival information from the intelligent parking system and make parking decisions and reservations before departure. There's no need to direct the vehicle to cruise in the network. Then after the gameplay, there's a questionnaire designed to collect respondents' demographic attributes, including age, gender, and their travel information. The survey also saves the game settings and all the players' decisions in the database, such as all the parking spots' location coordinates and all the attributes of the parking spot. For players' decision, it has driving routes in the conventional parking mode and the viewed spots by the player, and then finally the selected spot and all their parking cost and their on-time performance. In this study, discrete choice modeling is used to capture and evaluate the influential factors for parking choices. The data collected are used to develop 3 types of parking choice models, which are multinomial logi model, nested logi, and mixed logi model. After our analysis, the mixed logi model have the best goodness of fit, and the multinomial logi models have the worst performance. Therefore, our results analysis focus on the mixed logi models. This table summarizes respondents' preference towards several parking attributes and their relative sensitivity in the two parking assistant levels. So for the first variable, people prefer parking spots that are close to destination, and the sensitivity to parking location is relatively higher in assisted parking. And then for parking types, so legal parking spot or illegal parking spots, respondents prefer legal parking alternatives, and they are more sensitive in assisted parking. The interpretation is that players develop different parking choice habits in the two parking levels. In conventional parking, under short time limit, because they have to cruise around the destination and that costs time, then respondents may be more likely to choose illegal parking spots in order to be on time to their destination. On the other hand, the time pressure in assisted parking, where they just zoom in the map and select parking spot before their departure, the time pressure in this mode is much lower. Respondents usually select the ones with relatively low expected cost because they can compare all the parking spots, which are always legal parking spots, and that's why it's more sensitive to prefer the legal parking alternatives in assisted parking. The next one, looking at legal parking cost, most drivers prefer low parking rate, and they are more sensitive to legal parking cost increases in assisted parking. And there are similar observations for illegal parking citation probability, which is like a cost for the illegal parking, that people prefer low citation probability, and it's more sensitive in assisted parking than in conventional parking. So from the chart, it's obvious that the driver's preference sensitivity towards all attributes are higher in assisted parking. And it can be explained that the availability of parking information is crucial in terms of respondents' perceptions. For example, let's talk about the legal parking cost. In conventional parking, respondents try to gather parking information while they are cruising. They may select spots with the lowest parking cost from their viewed spots in the end, or select the closest spot to the destination under high time pressure. However, the selected legal parking spot may not necessarily be the lowest in the network because they did not explore all the spots. As compared to the assisted parking, drivers with full parking information can quickly locate legal parking spots with the lowest cost in the network. And that's why the sensitivity to the parking cost is higher in assisted parking. This table summarizes respondents' preference towards several parking attributes. Next one. For demographic attributes analysis, we found that although parking choice behaviors of respondents with different gender and age groups are similar in assisted parking, they're quite different in conventional parking. And the interpretation is that in assisted parking, respondents experience low time pressure, as I explained. So most respondents behave similarly and select alternatives with low expected parking cost that will also allow them to arrive at destinations on time. On the other hand, in conventional parking, respondents are usually exposed to high time pressure, and the estimated parameters indicate the respondents with different attributes react differently to the change in legal parking cost and the illegal citation probability. Specifically, respondents aged greater than 30 are less sensitive to legal parking cost and illegal citation probability. And the reason is that the respondents in the older age group have much higher income than the younger respondents in this survey who are students. And then for gender variable, it's found that the females are shown to be more sensitive to illegal citation probability than males. So more cautious driver. Then I want to talk about the mixology model used in this survey. The model is aimed to capture respondents' perception and preference heterogeneity of the alternatives, or the panel effect. It's observed that the outer illegal parking alternatives, which is alternative 4, shows significant preference heterogeneity only in assisted parking. In assisted parking, like the figure on the right, alternative 4 is often considered a feasible option to the respondents under the low time pressure. because it's a little bit far away from the destination as compared to the illegal parking spot in the closer region. And so people showing preference heterogeneity toward this illegal parking. Some drivers like it and the others dislike it. However, respondents may often consider alternative 4 as an infeasible option under high temperature in conventional parking, because they may consider under the high temperature, it's really hard to park there and arrive at the destination on time. Therefore, most of the respondents prefer not to select alternative 4, and resulting in relatively homogeneous preference, they choose not to park there, like the figure on the left. Finally, conclusions on the survey as a data collection tool for on-street parking. First, the survey is able to include less widely investigated variables without causing survey fatigue, because the travel simulator can visualize most of the variables, not just showing their values as text to respondents. For example, the time limit is shown as a live clock on the screen. The occupancy level can be visualized by the vacant spots by different colors. And the citation probability for the illegal parking is shown in different color schemes. Then second, the result prove the gamified simulation is effective, and it can therefore test the combined effect of parking assistance and other factors considered in the survey, like the enforcement level, the parking price, illegal parking fine, and the parking availability, and also the time pressure. The data for the two parking levels will be similar if the survey were done in a conventional state preference survey. It will be difficult to collect parking choice data under the two assistance surveys through a conventional question-based state preference survey. The data quality from the iCity Park survey is considered high because respondents tend to show their real estate parking choice behavior under simulated scenarios, and the data are rich because all respondents' decisions during the parking process are recorded, and they are useful for defining the choice set and thus more accurate model results. Then the results of the model and analysis show the respondents' perception towards explanatory variables, which are the parking spots attributes, especially their differences under the two parking assistance levels, which could assist future parking policy decisions regarding the provision of parking assistance. Definitely, there are some limitations of the gamified survey. Some respondents during the survey require installation guidance and training procedures for computer-based survey, especially the seniors. And the age may also be less motivated by the gamification incentive than the younger respondents. And lastly, for future work recommendation, in addition to the collected parking choice, the survey collected many other decisions that respondents made during their parking search processes, such as the view spots, driving routes, and the information gathering. So the richness of the collected data allow for developing many types of models that capture the dynamics of parking choice, the learning behavior of respondents as they become more familiar with the parking process, or the tendency that respondents to avoid wrongful activities such as illegal parking, regardless of the monetary incentives. And that's the end of our presentation. Thank you.
Thank you, Bo and Mehdi. We have time for a couple of questions. At the end of your talk, you mentioned other things that you might have captured if you were doing this. If you did a version 2, what other factors of parking behavior would you like to capture?
So there are many other factors that may have impacts on people's parking choices. For example, weather. It could affect the relative distance of the chosen parking spot, and people may tend to park close to their destinations in bad weather, such as heavy rain, and spots that are relatively far away may be considered in sunny and warm weather. Also, like visibility issue varies due to the weather condition, and it may affect drivers' parking search process, such as longer search time with low visibility. And the other things, yeah, sure. The other factor is the difficulty of getting into a parking spot. It may affect parking choices. For example, a new driver, an amateur, may not choose a parking spot between two parked vehicles with small room, and because it's challenging to get into and exit the spot. And another factor I can think about is the passenger in the vehicle, which may influence the parking decisions. For example, drivers with babies or seniors may select spots close to the destination just for the shorter walking distance. Thank you.
Yeah, just how painful is it to transfer an elderly person, somebody traveling with a child, and how much would that lead you to cut some corners, right?
Yeah.
I learned how to drive and park in Kitchener, Ontario, and it was a long time before I bothered to learn to parallel park. You just didn't have to out there.
Yeah.
I can't imagine, there's most days every journey begins with a step, with some walks, and many of our journeys include parking, and there's a few things more frustrating than looking for parking. Sometimes games can be frustrating too, but how real did people think this game was?
During the survey implementation, like most respondents provide positive reviews, and they think the simulated parking scenarios are really realistic. They mentioned that the two parking assistant levels simulate the real-world scenario well, because in conventional parking, just like in real life, they need to direct the vehicle in the network and to gather the parking information. And it is time-consuming, and this point is considered in the game. For the other one, the assisted parking, it's like using a mobile app to search and select a parking spot with navigations. They also feel that the money in the game is like the money in their real pockets, since the values are accumulated through scenarios throughout the game, and their values reflect their parking performance at the end.
All right, so it's a novel and easy way to go out and collect data on a fairly complex decision-making process that we all make every day. And I guess I know people who are different than I am. I'm the cautious parker. Here's one, I'll go take it and walk further. And I live with somebody who is always sure he's going to get parking closer to where we're headed. And I think it's all probabilistic, right? Yep. So you found that parking guidance is of value to drivers. Would parking guidance also have a greater public good in guiding drivers to parking? Not just about me, but about me getting off the road? Maybe?
Yes, it does, because I would say that when you don't know where the available spots are, you're more inclined to search. So you're cruising around on the streets. So these parking guidance systems have the ability of directing you to the available spots and just taking you off the road, if designed appropriately. Yeah, so they do have that advantage. I want to add to your first two questions regarding next steps, or how we could improve this app. I think this app was a great first step as a proof of concept. I would assume that one of the next things we can do is to model a more realistic city setting. Our setting was somewhat stylized because it allowed us to capture the behavior in the way we want it. But I think a really good next step would be to say, look at the city of Toronto and quote that and have people make decisions in that environment.
Which is something, in another step we would take up perhaps if we'd done this otherwise with Esri Canada, with their visualizations and see how, how does familiarity with an area come into this. Okay, thank you very much. We're going to move on to our next talk. It strikes me and bring up our next speaker. Oh, I wanted to remind you that the results of this work are posted on the iCity website. We're very proud of our brand new icity.utoronto.ca website, and we're posting here the results on the publications and presentations of this work, as well as the people who were involved in getting this work done. And I encourage you to go and check out the website. We'll be posting the game and the resulting work here. Okay, I'm going to bring up our next speaker, and she will join me. Thanks very much. It strikes me that another way to characterize the four talks that we're having today is that they all use novel and interesting creative ways of running surveys. And this is another example of that. Our second talk is Capturing Pedestrian Tours and Activities Through Smartphone Data, Lessons Learned. And our speaker is Ming Xiaomeng Xu. Ming is a PhD candidate working with the Waterloo Public Transportation Initiative, led by Professor Jeff Casello, who was her supervisor also in this work. Ming came to the iCity team after completing a Master of Community and Regional Planning at Iowa State University. Her interests lie in active transportation and its impacts on healthy and environmentally friendly neighborhoods and communities. Over to you, Ming. You can go ahead and take the screen. I'll pass it to you.
Well, thanks, Judy, for your introduction, and thanks everyone for joining us. Today, I'm going to talk about capturing pedestrian tour and activities through smartphone data. So we all know that there are a lot of benefits of walking. So it can benefit the public health, reduce emissions, and also promote social interactions. Also improving accessibility and the connections to the public transit by walking can also help us to promote public transit. So because of that, a lot of plans and policies are now trying to promote walking. So for mid-cities like Kitchener-Waterloo region, we also built our active transportation plans to promote walking. So I think it is the right time for us to address the impacts of the investment and policies towards walking. So to do so, I think we need a better representation of the pedestrians. So this is also one of the motivations for our study. And so we started from the conceptual framework. By using this framework, I'm going to introduce how we model and analyze the strategic level walking travel demand. I found it would be difficult to include all the concepts within one single slide, so I'm going to number those major concepts and break them into small sections. So first is we first started from household representation. We all know that people travel to accomplish activities. So within the household, there are a list of activities need to be done. So the household members and individuals travel to accomplish the pattern of activities while also minimizing their travel cost. So they can choose either motorized mode or active transportation mode. So unlike auto travel, walking travels have more interactions with the environment, both the natural environment and the built environment. So the environment or locational attribute can either promote walking or support walking. So once the environment can support walking, the household can choose different options, such as motorized mode and pedestrian tours. So here we consider pedestrian tour can also be an option to help us to accomplish activities. So to model them, we need some empirical data. The smartphone-based data collection methods can provide us opportunities to gather those empirical data in terms of the travel length, travel durations, locations, and the number of activities. So with those concepts, pedestrian tours can be further embedded and also put into the travel forecasting models, either non-motorized travel forecasting model or activity-based model. So let's take a look at the details. So the first thing we look is household utility. So we consider the household is the travel decision-making unit. They can make travel decisions in short-term, mid-term, and long-term. So the short-term decisions can be their daily travel patterns, when to leave, where to go, etc. And long-term decisions can be their workplace and home locations. And each person in this household has a set of activities for a typical day. Some of them are mandatory, like their school and work with a fixed schedule destinations. Some of the activities can be discretionary with a very flexible schedule and destinations and durations, or even can be deferred to another day. So the household also can have a set of shared travel resources, like their travel time, their budget, vehicles, and also their supervision for their children. So within the available resources, each person or individual can choose one of the travel modes to reach their destinations. Also, some of the activities on their list can be deferred or canceled if there is any time conflicts or no available resources. So if a household continue to defer and cancel their activities, it may trigger the long-term decisions, such as move to a new place or change their resources set, such as buying a new car. So to encourage walking, we need to satisfy a household walking travel need. So other than household utility, locational attributes can also influence their walking travel need. So suppose you live in the region Waterloo, in a suburban neighborhood, as the example on the left. So there's no walking site or grocery stores within the walking distance. So the only chance you can have a walking trip is the recreational walking. So all the other destinations you need to reach are really far away from each other, and you can only access them by auto. But if you live in the downtown or walking there, you can reach many different destinations very easily. You can still access to the recreational walking. You can walk from your home to grocery stores, pick up the kids from music lessons, and then return home. You can also access to the LRT stations, and even the GO train can take us to the downtown Toronto. So this area really allows us to accomplish many household activities by a single pedestrian tour. So here we think pedestrian tour as a function of household characteristics and the land use patterns can help us to improve the representation of walking travel behavior. So one of our goals is encouraging travel behavior move from case 1 to case 2. So we want to promote areas can provide more feasible, low cost, and multimodal tours that can satisfy household activities. So for example, the high utility destination areas with different desirable functions can, those areas can contain a mix of commercial, institutional, and recreational uses. Those can allow us and the residents to live, work, and play in the same area and move between those activities very conveniently by walking. So we are trying to model those concepts, but we are facing some challenges. First is we failed to consider pedestrian tours in satisfying activities because we don't have enough empirical data. And we also need to improve our travel survey design and most methods. And the current zonal structure cannot capture, they have some difficulties dealing with the short distance trips and walking trips, also the transit access and egress. So we also need to provide a better cost representation for the pedestrians. So we first started from the survey design. The conventional travel diary or paper-based questionnaires rely heavily on participants' memory, and most of the short walking trips are underreported because people tend to forget their short trips. So we propose to use passive data collection methods. The smartphone app can help us to record the entire travel patterns, and we also designed online a household survey to capture the demographic information. So once we have the empirical data, there are several defining characteristics of the GPS data observed during their travel patterns. So activities is the purpose of the travel. Also, it can be a cluster of GPS point at a certain duration. The trips are the purposeful travel between two activities. The defining characters can be their origin, destination, path, and duration. Also, stops can be either travel stops or activities. Also, tours are the sequence of movements starting and ending at the same locations. The involved characters are the activities and related trips. So to determine the activities, trips, and the stops and differentiate them, there are two things need to be done. First is identify when an activity takes place, and the second is differentiate travel stops from the activities. So before we started to extracting those key elements, the first thing we did is pre-assessment of the data. So we need to understand under what conditions does the GPS data work well, and what attributes of the GPS can be helpful in extracting those elements. So by comparing the self-reported data with the empirical data, we find and we think the GPS data is valuable to capture the activities. However, there are some certain type of errors we need to either remove from the data set or put them into the further analysis. So the most common errors is the inconsistent GPS data. As you can see, the example on the left is infrequent GPS reporting, and the example on the right is lost GPS signals, which can be caused by the smartphone app crash or app turn off. So those data or cases cannot support our analysis. So these several cases need to be removed from the data set. But there are certain types of errors not necessary to be removed, but need further analysis or process. The first example is when people enter the tunnel or the buildings, this might cause some loss of the signals. But after they walk out from the tunnels or the buildings, the GPS are continue tracking. So we can fill those gaps very easy. Another case would be trouble about LRTs. The high-speed vehicles can cause some missing data, as you can see the example on the right. But by overlapping the GPS data and the LRT routes, we can also fill this gap very easy. So another case would be the trouble includes drive-throughs. We need to pay extra attention because it's very similar to the short walking trips because they're really sharing similar characteristics. So those are the cases that we need further analysis or process. Once we have a clean data set, we can start to extracting the key elements from the data. So here we used 3 criteria to help us to identify activities from the trips and travel stops. So first criteria can help us to identify the potential activities by using the speed and time threshold. So for many activities, one would expect the participants to be fully stationary, such as sitting in front of a desk, have a meeting, exactly what I'm doing right now, or moving at a very slow walking speed, such as when shopping. So we consider a series of GPS points below the speed threshold can be a potential activity. And the second criteria can help us to identify the trips. So there are two components, distance and the bearing. So when a participant is traveling between activities, the path or the GPS points tend to reflect a directness in the travel. But during an activity, the participant's movements can be way much greater, in a way much greater circuitous. Also, the bearing can help us to measure the directness of the travel. If a series of GPS points constitute a straight line and the changes of the angle can be very small, then we are thinking this person is in traveling. But during the activities, the GPS data generate way much higher cumulative deviations in bearing than during travel. So the first 2 criteria can help us to identify the activities, the potential activities, and the trips, but we still need to differentiate the activities from the traffic stops. So the third criteria is the spatial identification of activities. There are also 2 components. It's the distance from the roadway network and the land use map matching. So we can use the example here. There are 5 potential activities from the GPS, can be identified from the GPS. Then we overlap with the roadway network. Then we can identify 3 of them are related to the transit stops. And also, then we overlap a layer with land use map. We can identify another 2 utilitarian activities. So to transfer the pedestrian tours and what we have learned from the empirical data into the modeling process, we need to classify and quantify the pedestrian tours. So by different purpose, the pedestrian tours can be recreational or utilitarian by different access mode. It can be unimodal and multimodal. So the example on the left is the recreational pedestrian tour. There's only one primary destination, their home. Also, the tour itself is the travel purpose. The example on the right is the utilitarian pedestrian tour. There are two different primary destinations and secondary destinations. Also, this pedestrian tour are accessed by transit, so it's a multimodal pedestrian tour. Also, complexity of the pedestrian tour in terms of the distribution of destinations, numbers, and sequence of the activities. So previous studies classify those pedestrian tours into single purpose at single destination, multi-purpose at multi-destination, and multi-purpose at single destination. So more importantly, we think the pedestrian tour is not only link the activities with the related trips, but also reflect the sequence, frequency, and duration of the scheduled household activities. It also can reflect the household characteristic and the built environment and the land use patterns. So how can we better represent the travel cost of the pedestrian tours? So we know travelers care more about activities and always trying to minimizing their travel cost by reducing the activity travel time. So in case 2, the travel cost might be lower than the case 1 because the high utility density area can support many different types of pedestrian tours. Once the pedestrian tour's travel cost is lower than the auto tours, the household is more likely to choose pedestrian tour instead of the auto tours. Here's some common observations from the pedestrian tour data. The first one is very common in suburban area. That is, people run with long auto trips followed by short pedestrian tours. That is, people drive from one location, park to the parking lot, go to the stores, accomplish short pedestrian tours back to the parking lot, and then move to the next store. So it's pretty common observation in suburban area. Also some cases that people use transit to access to the downtown area and conduct very long pedestrian tours combined with multiple activities and then back to the same location by using transit. Also similar like auto access to the parking lot adjacent to core downtown area. So now we can, with those concepts, we can link back to the conceptual framework. So for each household, individuals are generating their daily activity list, and also they are facing the scheduling constraints because of the limited household resources. And then once they have the activity list, we can check the built environment, whether it can support or not support their walking. The propensity to conduct those pedestrian tours or auto tours can be estimated based on the existing or proposed land use and the built environment characteristics. If the built environment can support the walking, then the empirical data can help us to identify the sequence of the activity and the complexity of the pedestrian tour. So the pedestrian tour can embed it into the model and help us to understand how they can complete the activity list. So the common goal here is pedestrian tour is helping us to complete the household activity list. So the long-term decision won't be triggered because now they have more choices. So for the future study, we hope we can continue our data gathering. The recruitment methods, we can reach people by reaching different neighborhood associations, local businesses, and organizations. We're also going to distribute flyers, posters, and digital versions through social medias. Also, we are trying to reduce the burdens of the battery consumption for the participants. So we're going to distribute portable phone chargers for our participants. Also, another ongoing project led by my colleague Pedram Fard is the dynamic activity zone. So as I mentioned earlier, the zonal structure cannot capture the pedestrian tours and trips. So we hope we can merge and the homogeneous adjacent segments, and to identify which areas can support, can be the high utility destination area and support more pedestrian tours. So I hope in the future, the transportation planning and the engineering professions can give active travelers same attentions as is given to other road users. So we can not only just increase the number of pedestrians, but also improve their walking experience and promoting the areas that can provide more feasible and low-cost pedestrian tours. So thank you for your attention, and back to Judy.
Thank you very much, Ming. And thank you for all the times you hopped on the GO train to come in and join our meetings at the University of Toronto. It was just always great to have you there. And what great work, because it's so important that we get a better insight into pedestrian behavior and how people use walking to achieve what they're trying to do. So we have some time to talk about that. I have a few questions.
For sure.
We've heard a lot about data privacy in this region. Lots and lots of talk about privacy and concerns over sharing of data of all kinds in maybe a so-called smart city. So what kinds of concerns did you have with the people who are sharing their location and intention data with you?
Right. I think the privacy issue is the biggest concerns from the user's perspective. And I think there are two methods that can help us to keep those informations in privacy. So I think during the recruitment process, we should clearly inform the participants that we're going to eliminate the first or the last 30 seconds of the data. So all the addresses will be aggregated into the postal code. And also their sign-up emails will be replaced by random generated numbers. The second is when storing the data, we also have to let them know that those informations are really stored in a secure database and with limited access to only researchers. So I think in this way, the participant may feel like, okay, my data would be in a safe place and in a secure, so I would like to participate more in this type of data collection.
And I guess in that instance too, you're going to tell them that you're collecting data between this time, this day and that day, and for this purpose.
I think the app also can let them to choose which day they can participate, and they have the opportunity to decide which data they are willing to contribute.
And meanwhile, we're worried on the one hand about data privacy, and on the other hand about inconsistent and broken up data that's coming in that is not actually very useful. So we know there are lots of, we have great expectations of data collected in this way, and lots of obstacles to overcome to make the data more complete. Right? I think I misspoke. You collected only location attributes, not information about what people intended to do. You imputed that from the data.
Right. I think for our study, we are looking at the pedestrian travel at the strategic level, also the household level, how they're making their walking decisions. But other factors like directness, road design, and sidewalks, pedestrian infrastructures are the attributes are more at the operational level. So if we want to include them into the model, I think we can break the pedestrian tours into segments and based on the homogeneity of the built environment. So we can say that those are also the attributes we're looking at.
And I did, as I said, I learned to park a car not parallel. Growing up in Kitchener, Waterloo, an interesting place because it's both with the introduction of the LRT, has a thriving downtown and big university college presence, and also as an established suburban community, right? So you have those two things to look at. So now that we've in this time of COVID and times of reopening and getting people going again, and with concerns about transit, certainly in Toronto, active transportation is being promoted as an alternative for people who can do it, to save space on transit for people who need it. And of course, we hope everybody doesn't hop in their cars, and there's not enough parking for everybody to hop in their car anyway. You didn't do this work thinking about circumstances like this, but how could we use information that you have, or what would you do to provide other insight into what we do to the walking environment to make it more attractive, more effective for people to use to satisfy their needs, that they can do them by walking?
Right.
We need more walking, at least in Toronto.
I hope so.
But can you think of, out of your research results, would you have advice?
Right. I think the planning process should not only just focus on the sites, but also focus on the areas, that how we can promote those areas to support more walkings. So I think from our data, we can, if we continue collecting their travel behaviors, I would expect that there would be more recreational walking. But once we are reopened to the stores and things like that, we would expect that more utilitarian walkings at high density and high diversity areas that can support different destinations and activities.
And you didn't work on cycling, but I know that University of Waterloo also the region of Waterloo also has a very, I don't know, say aggressive program, but an ambitious program to add to its cycling network.
Right. I think when we gather in data, we actually track the entire travel patterns. So I only extracted the pedestrian tours from the data. I think for the other part of the data can also be utilized in different research purpose. That I think that's for sure, because we are tracking their daily activity patterns, not only just pedestrian activities.
Well, I know there's great interest on our side on finding an opportunity to follow up with Ming and Jeff on the great work that they've done, because certainly facilitating pedestrian movements in the city of Toronto is important for us, for people who are moving around in the busy urban center, and also for people who are living along the busier arteries, and some of them using transit, but providing them with the means they need to get around by transit and other ways. And it's just a behavior we don't really understand very well in lots of people, and what will facilitate it, encourage more of it. So as I said, it was great that Ming came in to join us so many times.
Thank you.
We're delighted to have her along on the project. I said she was supervised by Jeff Casello, and at the University of Waterloo, this is what they do. And we will be arranging a time to follow up and see how we can bring lessons learned from Waterloo into Toronto. Thank you so much, Ming. And thank you, Jeff. Okay, again, this Ming's talk is a capstone talk on work that was conducted over the series of 5 years at the University of Waterloo. And you can find more information about Ming and Jeff's work on the iCity website. I encourage you to check it out. All right, on to another novel method of collecting data. Our next speakers and our third presentation. Our presentation is a dashboard tool for mapping and evaluation of complete streets in Toronto. We're back to Toronto. And our speakers are Dr. Greice Mariano and Professor Matt Roorda. Dr. Greice Mariano is a postdoctoral research fellow at the Visual Analytics Lab at OCAD University. She came to the iCity team after earning a PhD in computer science at the University of Campinas in Brazil. As an iCity postdoctoral fellow, she has been collaborating with the development of user-centered visualizations for iCity research. Matt Roorda is a professor of civil and mineral engineering, a Canada Research Chair in Freight Transportation and Logistics, and the chair of the Smart Freight Center. Matt's research interests, obviously, are mostly in goods movement, but thankfully, also in parking and complete streets. He brought to both projects his leadership and extensive experience in the development of new models and urban systems for both people and goods movement. I'll pass the screen over to you, Matt.
Okay, thank you very much, everybody. It's really a pleasure to speak with you today. I'm going to start just by giving a few minutes of introduction about a 5-year project that we have been working on, which has been a collaboration between University of Toronto, OCAD, Esri Canada, Waterfront Toronto, and many others who have been participating. And this is really to learn more about complete streets and really to work towards an evidence base towards evaluating and mapping complete streets. Today is mostly about Greice's work and her colleagues' work at OCAD on developing a dashboard tool. But I'm going to start just by giving a bit of an intro to some of the precursors to that work, which we've been doing over the past few years. So first of all, the motivation for doing this is really, we feel and we have heard from many different stakeholders that there is a tremendous need for an evidence base behind some of the decisions that are made about complete streets, and in particular the trade-offs that sometimes have to be made between how the space in a roadway is being used, particularly in those places where you have a constrained environment, constrained right-of-way, and only so much space to go around. So we've been working on the literature and looking at where the evidence base is weaker and where it's stronger. We found, obviously, and I think any engineer would know that there's a strong focus on throughput of automobiles and transit. Those are the engineering aspects of a road, but fairly little that we have found on an evidence base that really gets at the user experience, particularly for pedestrians and cyclists. So that's what we were motivated to try to do, and then to try to build these new pieces of information into a design toolbox and eventually a mapping tool that Greice will talk about. If you could go to the next slide. Yeah, so stakeholders, yeah, we have been participating in many different forums and so on, and this is just one example. It was back in the days of the planning for sidewalk labs, which is now not going to happen. But what we heard strong and clear was a message that there is a need for an evidence base and some basis for the really hard decisions that need to be made around allocating street space. Next slide. So our 5-year project really started with looking at what kind of empirical evidence is in the literature for complete streets. And in a few cases where we found that literature was fairly weak, in particular in pedestrian perception of how desirable it is to walk in a certain place, we built that evidence base using some survey and other data collection means. Then we built these into a toolbox, and starting with the engineering approach, we built it into a spreadsheet, and then we passed it over to the wonderful people from OCAD who have a lot of capabilities in graphical user interfaces and so on, who've been developing a dashboard. And I'm just going to talk a little bit about each one of these, starting with our literature review. This was the work of Nancy Hui and Shoshana Sachs, and then some of the rest of us at University of Toronto did a real deep dive into the empirical evidence base, and really found that there are elements to complete streets, including the ability of a street to fulfill its functional requirements of, having vehicles move, cyclists move, and pedestrians move. It's that movement function. Then we're also interested in the environment function, but then finally, there is the function of a street as a place to be, and that's really where we focused a lot of our energy, and in particular the walkability and user experience. Now, these things are easy to grasp if you're walking down a street, what's pleasant and what's not, but we wanted to really try to grapple with the empirical evidence base behind this. So next screen. So we started by designing a survey, and this was a really interesting three-dimensional animated survey. We came up with a statistical experimental design. It was an online survey of 600 respondents across Ontario. And the purpose of this statistical design of the stated preference survey was that we could develop a model of user preference for different attributes of a streetscape. Build that evidence base, which in turn is intended to inform planning. Next. So 600 respondents. It was a 3D animated environment and statistical analysis using mixed logit model with panel effects. Don't want to go to any of the details, but if we go to the next slide, it'll show the website where you can try this survey for yourself, and you can. It's really kind of interesting. There's 3D animations. It has you walking down the street. You make selections of which environment you prefer, and all done within a rigorous statistical framework. Next. So our third step then was to take everything that we learned from the literature and from some of our survey outcomes and try to design at least a spreadsheet toolbox that put all those elements together and developed a scoring system for complete streets that is based on the evidence and based on some of the methods that we had learned from the literature. And if we go to the next slide, it shows some of the inputs that were required for this model. And I'm going to not talk about this in any detail because Greice is going to come back and speak about these in detail. But you put in inputs about the widths of various aspects of the streetscape, pavement conditions, the traffic conditions, transit flow parameters, and so on. And then the outputs would be a scoring system, which are shown on the next slide. Right there. The fourth step in our research program was to develop this map-based visualization dashboard, which the intention of this was, rather than looking at one single streetscape, was to bring that information and be able to view on a mapping system the ability of roadways to be considered basically the scoring system shown on a map. And I'm going to pass it over to Greice now to complete the presentation.
Okay, thank you, Matt. Good afternoon, everyone. So as Professor Matt introduced it, I'm going to present the map-based visualization dashboard developed to support the UFT team on the evaluation of completeness of complete streets. So this is our team and UCAD and from UCAD from University of Toronto. We had the students Vida and Ming work on this design dashboard, and we had the support of Ibu, who developed the first interaction for this dashboard. So before I present the dashboard itself, I would like just to contextualize our work on this, because when we started this collaboration with the UFT, their team introduced us to a main question for this dashboard: what are complete streets? Because this is a really important thing for this this evaluation of the complete streets. So complete streets is a term used to identify streets that were built to safely accommodate automobile, pedestrians, bicyclists, everyone in a safe way. So though the complete streets idea is compelling, not every street can accommodate all types of the use. So it depends on the type of the street. And there is a lack of tools that Uber planners can use to make those evaluations and make sure if the streets can be completed or not, or what they can change or what they can do on those streets. So based on that, the UFT team introduced us this spreadsheet, and this is a video for their work. This was developed in Excel spreadsheet format, and the main idea on this spreadsheet is that streets can be analyzed based on a score computed using level of service. So in this first tab, we have all the instructions for the users, how they can interact with this. And the second tab is the input data, as Matt showed before. So here we have all the parameters that the user can interact with. So we have parameters like the transit, we have parameters related with the roadway specifications, And based on the interaction of the user with these filters, the visualization, the bar graphs and the gauge graphs, they change the level of scores. So how those scores are computed? So on this screen, on this spreadsheet and dashboard format, the user selected their parameters on the screen and visualize on the map. And on the next tab, who is the design tab, on the design tab, you have all the data informed by the user. So here is an overview for all selects that the user made on the input tab. And based on this design tab, we have six categories where we explore the level of services. So for each category, bicycle, pedestrian, transit, goods, auto, environment, and place, we have different ways to compute the level of service score. And we also are using the classification of the street, so we can also have identify what is the type of the street, if it's an arterial or a local. And based on all those values, we compute the score, and the level of services grade is used to make sure the computed score can be fitted as target, max score, or score. So basically, we have the worst scenario and the best scenario. And we have the real score computed for each category. So what we are showing here on the gauge, mainly on the gauge, you can see this minimum, maximum, and the target score. So, and the percentage is saying that if the streets is complete or not. The percentage represents the completeness of the streets. So the main idea on this dashboard they developed was to create a tool where to create a bridge between the governments and the urban design and make sure that the urban plans can optimize their process. And for us, when they gave us this opportunity to work with them, we saw that the functionality was really clear for this dashboard, but there was some visualization and some usability points and challenges that could be resolved and improved on that dashboard. So this study is basically trying to support them on how can we improve this visualization and make sure that this visualization can be helpful for the urban planners. So we divided our process in UCAD in 2 steps: in dashboard design and dashboard implementation. So the dashboard design was based on the considerations we found looking for their spreadsheet. So we found some problems like, for example, usability because the spreadsheet format, the scalability. So we just could look for one street, the universal thing, universal point of view, and if it is adaptive or for other cities or for other contexts. So based on those considerations, we defined an interface design approach based on main 3 principles. All of them are the user-centered approaches. So we use the first design thinking, where we have some stages that to understand the problem, to define the questions, to make some brainstorms with the user, and to identify the main points to create the prototype and test this prototype, get feedback, and start again. So this is the process to create the design. So we made this mainly with the Boo and Matt. We had some meetings with them to develop the final prototype. We also used the principles of usability proposed by Nielsen. So we thought in elements, we should use the elements that the users can interact and be easy to learn. It would be easy to remember, so the user can use this tool today, but 1 week later, they can come back to this tool and they will know how to use this tool. And finally, we used the user-centered design approach, thinking about the simplicity of the screens, the interfaces. The interface should be simple, clear, consistent, meaningful, extendable, and collaborative, because we know that urban planners don't work alone. They need the collaborative work. So we thought on this, how can we provide this experience for the users as well? So this is our final representation. This is a video as well. So to make sure that the users can collaborate with each other, we create a login screen where the user, and the first screen is a map view, so they can interact with all the streets on the area they are looking for. In this case, we are looking for Toronto, working with Toronto area. So they can filter the streets by their type or by their completeness, the values of the completeness. They can navigate into the map, go in, zoom in, or zoom out. We also have an option to search a specific street. On this case, we are working also with directions of the street. So we can have, for example, here we have Wellesley D. So we can have different directions where the car is going. We have the representation for this completeness, both in the map view and a different tab to show this completeness for each category. And the user also can explore how this was computed. So we put some research information as well. And at the end, the user also can edit all his preference. So here is the dashboard view, and the users can change all the parameters and save this. And they can see different scenarios for the same street. So they can see all the complete streets value changing, all the scores changing for each category in real time, and they can save this and compare, and based on their files, they can compare the different scenarios for the same streets with different data. So the user also can download this data. And when they finish these changes, they can go back to the map view and visualize all their changes. So this interface design was developed with a minimalist way. So we use the black. Maybe you can ask why you use black for the color. So we used black for the first time because we were interested to the user focus on the function and nothing else, and also to denotate the positive and the negative actions, because the graphs are representing those actions. We also use the clean fonts to make sure that it's readable for everyone. And we use the common elements for interface based on that can be responsive for web application, for mobile interfaces. In relation to the implementation, this is the data structure we had. So this is an example of the parameters we have on the dashboard screen, and we are using to demonstrate the completeness, compute and demonstrate the completeness. Here are the technologies we use for the front end and the back end. This was initially developed with open source tools. So we used the DACGL as a JavaScript library for data visualization. We use D3 as a JavaScript library for the graphic to create the graphics for the visualization. And in the back end, we are using mainly Python with Flask to communicate with the spreadsheet and get the data and make sure that we are showing the completeness of for each street. This work is about the design is going to be published on July in the HCI conference. So we hope share with you in our iCity website soon, and you can read more about this work. And our next steps will be, we know that this is a work in progress, so we still have to do a user testing with urban planners, because for us in this first stage, our users was the UFT team. So now we need to make tests with our final users that are the urban planners. we also need to go explore more the scalability, because we made for Toronto, but we worked with some hypothetical data. So now we need to work with other cities and the other numbers and make sure that they are real data and see how this will be. And it also work with the responsiveness. And at this moment, we are working together with Esri Canada to improve this tool and integrate the 2D visualization OCAD team have made with 3D visualization that ArcGIS has, City Engine and the ArcGIS platform has capability of to explore. So we are interested to make this integration and provide more experience for our final users that are the urban planners. So thank you, everyone. This is our the final of the presentation. Back to Judy.
Thank you very much, Greice and Matt. Greice and Matt presenting finally for a research project, as Matt said, that did run the full 5 years of the iCity research effort and culminated in work that we're very proud of with this dashboard and the survey that informed it. I'll start by saying I had a question posted that could we share the link to the survey. We won't go back to it, but I'll tell you that all the presentations will be posted on the UTree website as soon as they're more or less as soon as they're completed. So you will be able to check on the UTree website and find this presentation and find that link. And if you share your contact information, we'll get it to you faster. And eventually the survey and the dashboard will be shared on the iCity website, and you'll be able to take a tour of it also there. So all of this coming forth soon. Thank you for your question. Okay, so some other questions. I think this is very complete. What kinds of things do you think are missing? It was informed by a very comprehensive survey, a literature review, many ideas brought from the literature and experience. Greice, and you mentioned that your initial users were University of Toronto people. At the end of all of this, what's missing?
So for our proposed dashboard, I think when we had a meeting with the UFT team, we separated this design approach and the dashboard implementation in 4 stages. And the last one, it was the integration with this 3D environment. So this is one thing I think is really important and is missing for this dashboard. And now we are working together with Esri Canada to make this happen. Also, from the point of view for urban planners, I think a really important thing and to answer better your question is to make some user testing with the urban planners, because from them we will get the feedback and know what exactly we need to improve or what is missing in our tool right now.
So go ahead.
I can add to that as well. I think there are still lots of things that we don't know about people's preferences and about sort of trying to define a street as a place that people want to be. So we did this survey, and it was a really great experience, and we did our best, but it's still limited to only certain aspects of the roadway. We were looking at the allocation of the meters of roadway width that would be allocated to different functions, like bicycle lanes versus wider sidewalks versus parking versus putting in trees. But I think that there are so many other elements of context that really matter that just require more research, more different ways of looking at it. For example, people will have very different preferences when the weather is different, and people have very different preferences if their purpose of travel is different. If they're trying to commute, then they're going to be thinking about the place they're walking in a different way than if they are shopping. And so I think there's still a lot to learn, and we have put a lot of effort into developing this dashboard tool, but still the underlying research behind it needs to continually improve. And
maybe a tool like this will facilitate that, because You know, in these kinds of projects, we're not, as much as Greice talked about a process that they followed, the iterations continue, right? As you show somebody with some expertise, or even a user of the street, you know, what the assessment of a street they know, right? They can compare that with their own knowledge and say, I think you're missing something.
Yeah, and there's other people as well. People who have physical disabilities are going to completely view it from a different way of thinking. Cyclists, we haven't done a lot of work on cyclists. It's just, we only had so many years to be working on this and so many resources, but there's so many other things we could do. I think intersections are another thing that needs more work.
I mean, I would say who knew, you know, so I've said it before today, who knew how our streets would be changed in the last several months? And streets now, as you talk about places, for a street as not just a place for people to move along in whatever way they move along, but also of places to be, as we have fewer and fewer places to be. So we're out there. And I know people are congregating outside some of the social clubs in my neighborhood, standing on the sidewalk 6 feet apart on either side of the sidewalk, using that as a place to be because they can't be inside and they're used to being together. Absolutely. We choose Harvard Street for our walks, walking against traffic, because we can step off into the bike lane as pedestrians, which wasn't considered as a good use of that cycling lane till it became a necessary use of that cycling lane.
Yeah, absolutely. I think we view our sidewalks in a different way when we're social distancing, for sure.
Yeah. Well, and then, you know, the difference between the different seasons, which we understand oh so well. If we had another thing we could do with this project, if you'd had just a little bit more time, Greice, what would you do next?
I would start with the user testing for sure, because it's really important to think for this application, and also make this accessible for other people as well, for they can see. And I know we are using some terms, specific terms, so maybe we needed to think how can make this accessible for the public in general, but I think this would be other way to get feedbacks as well. So yeah. Just
more consulting. And I guess I should mention too, when we begin the work with, you've begun the work with Esri Canada to have this implemented in their software, and when we do that, all of the information we have on the current built form will be the accurate distances of, widths of, placements of, because they have all of that data.
Yeah, and we are on this point, when we developed this dashboard, we had some gaps of data. We don't have all the data, as Matt mentioned. We have some points that we need to still explore and find out how we can get those data and input on this dashboard. Because for right now, we don't have all the information. So we are working together with Esri as well to think about on these things and how can we.
And I can imagine that this is definitely one of those build it and they will come. If it's useful, we'll get the data to complete this work. And we have been excited about this work for a long time and really glad to see it come to this kind of a fruition. And it's a great example of our collaboration. Thank you very much.
Thank you.
Okay. And you will find this work again on our iCity website. And if you haven't figured it out yet, the iCity website design also brought to us courtesy of our partners at OCAD University. Thank you very much for that. Okay, our fourth and final talk of the day. I mentioned in my introduction that all ORF research projects must have a youth outreach program, and we created ours in partnership with our youth outreach partner, the excellent Maximum City. Through collaboration with Maximum City, iCity's youth outreach program has reached hundreds of local and international middle and high school students participating in Maximum City's annual summer and March break programs. The work they're going to present today is their own. We like to think it came out of our collaborations and the joint development of our curriculum in Complete Streets that they presented in their programs. Now, Maximum City is headed by Josh Fullan, who brings over 15 years of experience of delivering successful projects for governance, communities, and private enterprise and public consultation, community facilitation, education, and engagement. In 2019, Josh acted as project lead for the City of Toronto's KidScore pilot. We're talking about KidScore today, and was the strategic advisor for the City of Toronto Children's Services Strategic Plan. Obviously interested in our KidScore. He is currently leading a national study on the impact of COVID-19, social and physical distancing on Canadian children and youth. KidScore is another great collaboration with our partners at Esri Canada. Susie Saliola is an education and research GIS analyst at Esri Canada, where she provides support for various teaching, learning, and research projects, facilitates workflows for all levels of GIS users, and works with different partner organizations to create meaningful maps and apps. Susie has a special interest in using GIS for community research, engagement, and development.
Thank you, Judy, and thanks to Pat and Judy and the iCity team for organizing this. It's great to hear the other projects present, and to sort of pick up on Judy's point, yes, the commonality, I think, is using surveys in interesting ways to collect data and engage stakeholders. So I am going to chat about the KidScore and run through a pilot we ran for the City of Toronto last year. And if you know what a walk score is or a bike score, then you kind of know what the concept for a KidScore is. So it's essentially an assessment tool that measures the child friendliness of urban places. What's unique about our tool is that the criteria come from kids. So we spent a couple of years, partly with iCity partners, sort of developing criteria and going out to kids and asking them what made for good urban places, what made for happy and healthy neighborhoods. And we used that information to develop the scoring and the weighting in the tool. And that image you see now is part of the data collection process. So we give kids these sort of caption tags that they go out and they tag their likes and their dislikes. And then they fill out a survey tool at the end of their neighborhood exploration, and that produces a score out of 100. So in a nutshell, that's what the KidScore is. But I want to get into a little more detail, and here's sort of a flow of what I'm going to show you. I'll give you a longer introduction to the tool itself, talk about that pilot program with the City of Toronto, which collected some really interesting data that they're now using to inform their child-friendly TO initiative. Talk about some of the uses of the data and maybe a few limitations as well. We've got some really nice visuals, maps, and findings that I can show you from the pilot. Talk about the conclusions. Then I'm going to hand it over to Susie from Esri, who's been sort of the technical expertise throughout a lot of this, and really produce a fabulous interactive map that shows how kids interact with their infrastructure throughout the City of Toronto. So what is the KidScore? It's, as I said, a survey and observation tool that evaluates the child friendliness of urban places. It was developed by children and youth and experts with the input of experts for children, youth, and policymakers. It has quantitative and qualitative attributes in the survey responses that produce an overall score out of 100 and then 5 subscores in different categories. And those are the categories. And we came up with the language for the categories, but as I said, it was really kids who told us, you know, these are the things that are important to us in neighborhoods to make for child-friendly places. And we kind of grouped them thematically by those places. And they probably are not surprising for anyone kind of who works in urbanism. These are kind of the buckets that we typically see. The sort of differentiator is some of the subscores, some of the categories are weighted in a way that emphasizes what kids value. So there is, it's not just a one-for-one weighting within those subcategories. The pilot we conducted last year for the City of Toronto was for Children's Services and for Public Health. The contract sat with Children's Services, but it was really for both of those divisions. And the goal really was to, after all this research and development of developing the platform, was to actually implement it in the City of Toronto. So we engaged about 250 kids ages 6 to 9 in 9 diverse locations. And we were really intentional about where we did these assessments in the pilot program. So where the criteria were quite extensive, and we put a lot of thought into them, and we thought about things like different built forms, different socioeconomic backgrounds, different kind of school settings. All of those things went into the criteria selection so that we came up with a good spread of different places to assess, so that, you know, we had a good basis in the pilot to move forward with. And the data and the findings now are being used by the city's interdivisional child-friendly TO initiative. And that sort of the focus of their work is to apply a child-friendly lens to all of the city's planning and policy work. And they have representatives from probably about a dozen different divisions, including children's services and public health. And, you know, a lot of the obvious ones that you would think of that serve kids' needs, you know, parks, forestry and recreation, planning. And they work to apply that child-friendly lens to all of their planning and policy work. And the report from the pilot was released in March 2020, and the timing in some ways was challenging because we had a big plan to sort of roll out the report and also scale the KidScore platform itself. But as we know, we sort of pressed pause on a lot of engagement and in-person activity since COVID. So that a lot of that stuff is still on hold. And it is worth mentioning that in terms of the age cohorts that we worked with, for the pilot, we worked with ages 6 to 12. But we do have a separate tool called the U-Score that we've used with 13 and up. So it's hard to do it with really young kids, you know, toddlers, but you can do it with 5 or 6 year olds right up to 12-year-olds. And then the separate U-Score tool, which has slightly different criteria that older kids value compared to younger kids, is for that older cohort. So the process that we followed in the pilot was kind of consistent across the 9 communities, and it started with a short individual place-based well-being survey. And that was something that kids would complete in a classroom or a community center setting, and it really captured baseline feelings about place and individual well-being, and also got kids thinking about the things in their neighborhood and how those things made them feel. And then I would say that sort of the key activity in the process was this guided walk. For the pilot, we participated as facilitators for all of the guides, but it can be done independently. The walks can be done independently as well, but for the pilot process, we participated as facilitators for the walk. And in that sort of 45 minutes to an hour, kids explore, they observe, and they collect data and take photos of a specific area that is going to be assessed using the tool. And when the walk is complete, the kids have an opportunity to complete the survey using Survey 123, an Esri tool, to assess the area they walked, and then it produces that score out of 100, and the score gets mapped spatially. And then fourth sort of step in the process, and we didn't do this with all of the communities, but certainly we left the resources, kind of a toolkit for all of them to do it, was a design challenge. So the kids could look at the overall score, they could look at the sub-scores and where their communities were doing well in terms of child friendliness and where there were opportunities, and they can actually pitch changes and make a sort of a new design for those neighborhoods, whether it be a better street or a better park, better connections, more safety, and then present those to kind of decision makers within their area or their ward. And these next series of slides just sort of show what the observation and the data collection process looks like. And it's really, there's a strong element of just getting kids out into their neighborhoods of the KidScore. So it's about creating connections or strengthening connections that kids already have within their neighborhoods. Some of them had strong connections already. Some of them really had not been out in their neighborhoods much at all. So this was an opportunity really to discover their neighborhoods. And another thing we discovered was that green space was close to a lot of the neighborhoods that we assessed, but kids didn't always, they knew it was there, but they didn't always access the green space. So this is in northwestern Etobicoke. And we conducted the KidScore with a group of grade 4 and 5s at a school near the Humber River Ravine. And many of the kids, in spite of the fact that this location was, you know, a few hundred meters from their school, had never been into the ravine system. And of course, they enjoyed it when they went down there, because you can see sort of the beauty and sort of the natural oasis of the ravine system there, but many of them had never been down there. So it's also, you know, the KidScore process sometimes reveals these gaps in neighborhood experiences that kids have. And then we just have some other images here of the process. Construction, which is, you know, sort of a fact of daily life in a city like Toronto, was really a pain point for kids. I mean, they found it, they always found sort of crossing a street with construction very difficult, felt very unsafe for them. You know, these things like Jersey barriers or pylons that push them out into the street was always a difficult thing. And that was something that would lower the KidScore of the neighborhood if that came up. And then public art was a big positive. So if there was public art, that would tend to raise the KidScore because kids would appreciate that element. So in terms of how the data can be used, it's worth pointing out that the data collection is done by kids, for kids and policymakers. So there is sort of a bias built into it. It's about kids' experiences, sort of a point in time assessment of how kids see a place when they explore a neighborhood. It measures how urban design, place, and social contexts are meeting the social, emotional, and physical needs of kids, provides a snapshot of how that location is doing from young people's perspective. It's not data that can be generalized about a neighborhood, at least not at the amount of data that we have right now. It does help identify citywide trends and address local gaps in child-friendly planning and policy. And it's really good at sort of talking to other data sets, you know, complements other data sets to inform local and citywide planning and policy. So if you're familiar with some of the other data indexes or sets that the city has for kids and families, Raising the Village is one. So the KidScore data is very complementary to Raising the Village or Wellbeing Toronto. That's another data set that tends to talk really well to what we've collected. And then in terms of how it can be used, the KidScore really does tell a unique and different story from what is presented in other forms of quantitative data. It sort of fills in parts of the missing narrative for different city agencies and divisions, provides them with an evidence-based tool for informing child-friendly policy and planning. The data in the spatial map show how kids interact with social and physical infrastructure. So there are lots of maps out there that show infrastructure, but there aren't a ton of maps that show how people interact with infrastructure. And there are even fewer that show how kids interact with infrastructure. So that's a sort of a really valuable use of the map and the data together. And over the long term, the KidScore can track the impact of investment or neighborhood change from a child's perspective. So you can do point in time assessments and see how that KidScore might be changing after an investment or neighborhood change. The kid-focused goals of the KidScore, there's a strong element of engagement in education. So it's really about helping kids develop civic skills. And as I said before, a strong element of social cohesion as well, connecting children to the people and places where they live, play, and study. And there's an element of child rights too, sort of amplifying child voice, increasing child participation, recognizing that they are valuable stakeholders and their input matters. And all of these things contribute to their well-being as well. And in terms of what kids tell us about the KidScore experience, it's overwhelmingly positive, and I'll just kind of focus on that first one, that first quote on the to see how we feel where we live. So there is sort of an element of affirmation that kids experience if you go to their neighborhoods, talk to them about how they feel about their neighborhood, what they like and dislike in their neighborhood, because they don't usually get asked to participate in that kind of process. So right away, there is an element of sort of raising their voices and playing to their strengths a little bit. The other common thing we hear about is that the KidScore taps into kids' sort of natural sense to better the world around them. that there's their sort of inclination to be agents of social change. So this kid from Scarborough said, I want to make Canada a better place. A good place to start is in your neighborhood, and the KidScore was kind of the tool that she could use to figure out how to improve her neighborhood. And then this next series of slides are just sort of the visual representation of the KidScore data from the pilot. I'm not going to speak to the maps directly now because I have a couple of other slides just as we round off that pull some of the highlights from this data, but you can see the 9 locations listed in the table there. We chose intersection names, even though the kids explored all around sort of the intersections. We didn't want to use neighborhood names because that was sort of too large of a scale. We didn't want to use school names because we thought, even though we worked closely with schools, and we thought that the intersection was sort of the best way to identify it. And each of those clusters or circles represents a number of surveys completed by groups of kids, and the overall score is an average of what the KidScores produced in that cluster were. So there might be 5 or 6 survey points within each cluster, and that was the average score. And then for each of the sub-scores, there's you can see the range of scores here. Spaces and senses, uses and activities, green space and environment, and then finally safety and well-being. So I'm just going to breeze through that slide right there because I want to talk about some of the sort of highlights from those maps. So the average KidScore across the locations assessed was 45. So that may seem like a low score to you, but I think it points to the fact that kids' experiences of cities can be really different from adults, and they value different things. I mean, it sounds banal to say it, but they have different knowledge about cities than adults or other cohorts do, and they experience cities differently. And this is sort of they're authentic in different communities. The highest kids which was attributed to the Bathurst and College area. So if you know Toronto, that's sort of in and around Kensington Market. And that area scored particularly well because it had a lot of sort of attributes that kids like. So there are parks, there's lots of people around, which made them feel safe. There's lots of good mobility options, which gave them a sense of independence. So all of those things contributed to that area's higher score. And then the low score was 35, which was recorded near the intersection of Avenue Road and Eglinton. And the big thing that pulled the score down there was road and pedestrian safety conditions. The kids walked along Avenue Road, which can be a very unpleasant experience for a pedestrian, particularly a small pedestrian. And again, lots of construction in that neighborhood. So again, it may be counterintuitive to think that a neighborhood around Avenue and Eglinton, which had the highest median income of any of the neighborhoods we assessed, actually had the lowest score. So again, it sort of highlights the differences between what kids see and what some adults value. And the highest category subscore was 70 for green space environment at Kibling and Albion in northwestern Etobicoke. And again, that was that image of the Humber River Ravine that I showed you, and there's a long linear park, Massey Grove Park up there that the kids walked through. And those were very important positive attributes for kids. And just a few more findings from the pilot. We discovered that more than 75% of kids across all locations would prefer to walk or bike to school. So about 39% take active modes. Most of them walking. I think the bike share is at less than 1%. But more than 75% would like to walk, bike, or roll, which I think is sort of a powerful. There's sort of an appetite there for for planners and programmers to meet if they can create safe, easy choices for families to bike or walk to school. The appetite is there. More than half of kids who saw bike lanes in their location also saw a car parked or driving in the bike lane, which is, which again is something that is perhaps very Toronto specific. When we see the sort of the behavior on the road, these are things that are definitely active transportation, or parents who are making that choice makes them reluctant to make that active transportation choice for their kids and their families. Location scored highly for public transit, mostly because of buses. So buses really did a lot of the heavy lifting for mobility in these locations, and kids recognized that in their assessments. And then this one we thought was really important, was that knowing your neighborhoods and your neighborhood correlates to increased feelings of well-being and independence. So kids who said they knew their neighborhoods, that they knew people in or who lived around them, and they spent time getting to know them, also reported increased feelings of well-being and independence. And then this is just one concluding slide before I hand it over to Susie to talk about the web app. So the KidScore can help uncover differences in how kids experience a neighborhood compared to some adults. Kids have different knowledge. Again, it sounds very simplistic, but it bears repeating and sort of absorbing. The KidScore provides an evidence-based foundation to encourage city builders and policymakers and decision makers to plan and program neighborhood attributes that are kid-friendly and not just adult-friendly. It can be used by children and their allies in a variety of settings and across neighborhood types. And it can help city builders learn from and celebrate all neighborhoods. So that rounds off sort of my part of the presentation. I'm going to skip these recommendations and turn it over to Susie. If you want to grab the screen, Susie, and I'll come back and do a concluding slide.
I'll spend the next few minutes just talking about the KidScore app itself and how it was created and some of the technical aspects to it. This video here shows a super sped up version of how we created the survey app. I wish I could actually work this fast, but I can't. So on my end, I helped to provide support for Josh and his colleagues to create the KidScore app in Survey 123 for ArcGIS, which is an Esri tool. Survey 123 on the front end looks really similar to any other survey app that you might have used, but on the back end, when someone fills out and submits to your survey, the results of that survey will automatically appear as a point on the map in ArcGIS Online almost immediately. Another great thing about this tool, which you can see on the video right now, is you can code your survey responses. So basically each answer to each question is assigned a score. And when someone presses submit, those scores are automatically added up. And Survey 123 spits out that final score for the kid friendliness of the area. So using this tool, we cut out a lot of time. We don't have to export the data to Excel, do all of the coding manually, and then bring it back into a map. It skips all of those steps, and also it can feed directly into live updating dashboards like this one, as well as other maps and web apps. So this is the web app that was created to share the information from the pilot project. And it was created using Web App Builder for ArcGIS. And once you visit the app, you see a splash screen here. To make it as user-friendly as possible, there's a video that shows you exactly how to use the app, another sped-up version of work. And so once you view that, there's some more information here. You press OK and the splash screen goes away. There's also more information about what each button or widget does, again, to make it as user-friendly as possible. So if we were to open the legend here, you can see the clusters, the round circles show different clusters of where the survey was filled out to those 9 different locations. And you can see the darker the color means the higher the KidScore, and the lighter the color means the lower the KidScore. You can zoom into different areas, and as you zoom in, you get a little bit more information. So you can see here that there were actually 4 surveys conducted at this area, And the dotted line represents the walking route that the kids took through their neighborhood as they filled out the KidScore survey. If you click on one of the points, you can see a lot more information as well. You can see the location average as well as the city average, so you can see how it can compare for the overall KidScore as well as the 5 sub-scores. So if I was a decision maker, a policy maker, I could come here and see what might be needing a little bit of extra attention in terms of kid friendliness of the space. I will zoom back out, and there are a bunch of other buttons that I can quickly go through. There are other layers that are also available built into the app. So for example, Toronto neighborhoods, neighborhood improvement areas, and median household income. So if you wanted to examine that relationship between KidScore and median household income, you could do that. You could also, we've added the capability for you to add your own spatial data. So if you did have data already published in ArcGIS Online, you could search for it and add it, or if you have CSV files or KML files, you can add it to this app and overlay and see what kind of spatial relationships exist. The filter widget is just an easy way for people to zoom in and out of different neighborhoods instead of panning around, maybe if they're using a mobile device. And we've also added the capability to look at the data in a tabular format. So sometimes that's a little bit easier if you wanted to look at a quick summary, it's here. And this also filters by map extent. So if you wanted to see the results of 2 neighborhoods, for example, you could do that and use this table and maybe even export the results if you would like. I think that's kind of a whirlwind example of how you could use the app. So all of the points here were collected using Survey 123. So essentially, if someone were to be filling out this survey right now and submitted it, those results would automatically appear on this app and displayed and symbolized in the same way as well. So I think that's everything from me. Back to Josh for some conclusion.
Yeah, I just see that we're running out of time, so I'll just say if you want to give the tool a spin, just go to maximumcity.ca/KidScore. So all of the, we've actually opened it up so anyone anywhere in the world can do it, and there's a step-by-step guide at maximumcity.ca/KidScore.
Thank you very much, Josh and Susie. Your closing comment kind of anticipated my question. Which was, are kids just kids everywhere, or and can this KidScore be applied everywhere?
Yeah, so it's interesting. We've done it. We facilitated the experience in 3 different places globally. So Toronto, obviously, Frankfurt, Germany, and Shanghai, China. And those places are pretty consistent in terms of what kids value and in terms of how the scoring works out. The thing we don't know and we want to know is how it works sort of in other places like mid-sized cities, in suburban locations, in exurban locations. And that's sort of the point of opening up the tool now, is to collect data from different contexts. And then in 6 months or a year, when we have a whole bunch more data, we can kind of press pause and take a look at how different contexts and different locations globally contribute differently to scoring child-friendly neighborhoods.
Excellent. I think with that, I have to say thanks.
Sure.
And we move on. For me to say, I hope you enjoyed today's talks, and I hope you'll be able to enjoy us for our last talk of this series on Wednesday, this coming Wednesday. You can register at the U-Tree website. Our last section is called Long View, a longitudinal analysis of urban growth and transportation network expansion and next steps, which is a preview of iCity 2.0, urban data science for future urban mobility, our next project of collaboration with our partners at OCAD University and private and public sector partners in our region. I think you'll agree that the true value of our multidisciplinary academic government industry collaboration is really apparent in the outcomes you saw presented today, and we look forward to having more of those in iCity 2.0 I hope you will join us. As I said, you can register on the website. And all of the presentations that have been given to date will be posted on the UTRU website. You can see them there. And as I said, eventually on the iCity website. Thank you very much for joining us. We're sorry we haven't been able to host a symposium, but we're grateful that you were able to join us virtually. Thank you for joining us. We'll keep you posted as good things continue to happen at iCity. Thanks and goodbye.